It's astonishing how Africa and Europe are almost within touching distance, yet for over 1,000 years, attempts to bridge this gap have ended in failure. The narrow stretch of sea that separates these two continents, known as the Strait of Gibraltar, has become a place shrouded in mystery and danger. What makes this region so terrifying? Join us on this spine-chilling episode as we uncover the dark secrets and formidable challenges that make building a bridge from Europe to Africa an impossible dream. Voyaging across two continents. The Strait of Gibraltar links the Atlantic Ocean to the Mediterranean Sea and is about 37 miles long. In some parts, the strait is narrower, which makes these spots better for building a bridge. The width of the strait varies between 9 and 27 miles, but building a 27-mile bridge over water would be really hard. So, it's smarter to build a shorter, more reliable bridge at the narrowest part of the strait. Spain is only 8 to 9 miles away from Morocco's coast, which is just a 13-minute drive. Back in 1979, Spain and Morocco created a joint committee to explore the idea of connecting the two continents. This idea grew into a bigger project called Euromed Transport. Since 1981, the Spanish government has even backed a corporation focused on studying and promoting future connections between the continents. But the idea of a bridge being useful came up much earlier, even before these committees and projects. Even with all this planning, there's still no bridge or tunnel. Is it because of technical difficulties? Nope. We actually have all the technology we need to build this bridge today. Remember, the distance would only be around 9 miles, which isn't too long for a bridge. In fact, there are already several bridges around the world that are longer than that. For instance, the Chesapeake Bay Bridge Tunnel is 15 miles long. They found a narrower spot to build it, even though the bay is 30 miles wide. South Korea's Incheon Bridge is 13 miles long, China's Shenzhen-Zhongshan Link is 14 miles long, and the causeway across Lake Pontchartrain in the USA is 24 miles long, making it the longest bridge over water. So, building a 9-mile bridge across the Strait of Gibraltar doesn't seem too hard compared to these giants. And it's not just an opinion. Engineers agree. There's already a realistic design with deep supports, towers nearly 3,000 feet high, and a span of over 16,000 feet. The cost of this bridge would be around $15 billion, which isn't too expensive when you think about connecting Africa's 1.5 billion people with Europe's 150 million. A bridge like this would be used constantly. Studies show that this project makes sense both economically and socially. From a safety perspective, connecting the two sides of the Mediterranean would be a huge improvement. Right now, they're only connected by sea, and reducing reliance on sea transport would be a big step forward for trade. Bad weather can mess up shipping, but a bridge wouldn't have that problem. The benefits for trade, tourism, and migration routes would be huge. Plus, it would create tens of thousands of jobs, not just during construction, but also after the bridge is built. So, if this all sounds so good, why hasn't the bridge been built yet? Monster waves. Building a bridge across the Strait of Gibraltar faces several big challenges, mainly because of the tricky geography. First, there are powerful currents and tidal flows. The narrower the strait, the stronger these currents become. They make it hard to build a stable bridge or tunnel, and even ships need to navigate carefully. The strait is full of dangers, like the rapid evaporation of water and layers of seawater with different densities and salinities. Water in the strait moves constantly in both directions. The Mediterranean Sea sends a smaller amount of deeper, saltier water westwards. This is called the Mediterranean outflow. At the same time, a larger amount of lighter, less salty surface water flows eastwards. This is the Mediterranean inflow. Sometimes these flows can be interrupted by temporary changes in tides, depending on the moon and sun. At the far western end of the strait is a shallow area called the Cameronal Sill. This shallow spot limits how much the colder Atlantic water mixes with the warmer Mediterranean water. The Mediterranean water is so salty that it sinks below the incoming Atlantic water, creating a very salty bottom layer. This layer flows out into the Atlantic, but it takes a long time to mix fully with the Atlantic waters. You can trace this salty layer for thousands of miles from the strait. The strait often produces internal waves, which are waves at the boundary where two water layers meet. These waves form when water flows over the shallow cameronal sill. When big tidal flows come in and the tide changes, internal waves are created and move eastwards. Sometimes these waves are too deep to see at the surface, but other times they can be seen clearly in satellite images. These waves can travel for up to 100 kilometers and can interact with other waves, creating interesting patterns, which can be huge, sometimes reaching heights over 330 feet and stretching 1 to 2.5 miles. These waves are so big they can even be seen from space. So how do you build a bridge in such tricky conditions? Maybe a tunnel would be a better idea, but that brings its own set of problems. Terror of nature. The Strait of Gibraltar is like a big crack between two giant pieces of Earth called tectonic plates, the African plate and the Eurasian plate. These plates are always moving, and because of that, earthquakes happen a lot in this area. In fact, just recently, a special tool noticed 183 tiny earthquakes in the Mediterranean in just one day. Most of these shakes are so small that people hardly feel them, but they can still affect buildings. Parts of Spain near the strait are especially known for having more earthquakes. In 1960, not too far from the strait in Morocco, there was a very big earthquake. It had a magnitude of 5.8 and was very close to the surface, which made it really strong and destructive. It caused terrible damage, with around 12,000 to 15,000 people losing their lives, and many more were hurt or lost their homes. This earthquake was one of the worst in Morocco's history. Building something like a bridge here is tough because the area is not only shaky, but also has a tricky underwater landscape. If you could drain the water from the strait, you'd find a mix of deep valleys, tall peaks, and even mud volcanoes, all shaped by the flow of water and the shifting tectonic plates. Back in the 1930s, people even thought about building a tunnel here, but they had to give up because the rock at the bottom was too hard to dig through. And to make it even harder, the narrowest part of the strait is also the deepest, going down about 3,000 feet. Besides these challenges, there's also the need to protect nature. The Strait of Gibraltar is a beautiful place where you can spot whales, dolphins, and migratory birds. It's important to think about how big projects can affect these amazing animals and their homes. Matching modern innovation and rising demand. Building a bridge across the Strait of Gibraltar is no simple task, and there are many things to think about. For starters, the strait is one of the busiest sea routes in the world. Every 5 minutes, a big ship sails through, along with countless smaller boats and yachts. If construction were to block the strait, it would stop global maritime trade, which is crucial for moving goods. The strait sees about 120,000 ships each year. In comparison, the Panama Canal has around 13,000 to 14,000 ships passing through annually, and the Suez Canal has about 20,000. Both of those canals are man-made, while the Strait of Gibraltar is a natural passage. Another challenge is the need for the bridge supports to be strong enough to handle the occasional ship collision. Ships can and do bump into things, so the bridge has to be built to withstand these accidents. Plus, the bridge has to be high enough so the largest ships can pass underneath. This means construction must be carefully planned to avoid disrupting the constant flow of traffic. Stopping all these ships, even for a day, is simply not an option. One idea was to make a drawbridge, but that wouldn't work because it would have to stay open all the time, which would be useless. To figure out how high the bridge needs to be, think about container ships. These ships have been getting bigger since the 1980s. Bigger ships mean bigger profits for shipping companies, but they can also cause bigger accidents if something goes wrong. The largest container ship right now is the MSC Arena. It's 1,312 feet long and 200 feet wide. For a sense of scale, that's almost as tall as the Empire State Building if you leave out the spire. Ships like the MSC Arena regularly pass through the Strait of Gibraltar. When designing the bridge, we need to consider how tall these ships are, up to 230 to 260 feet. Even though some of this height is underwater, it's still a lot. Ships keep getting bigger, so the bridge has to be high enough to let them pass. Building a bridge here is theoretically possible, but it would be extremely expensive. The cost of such a project is very high. Finance and political tensions. Building a bridge across the Strait of Gibraltar is extremely expensive. Right now, it costs about $80 million to build just 6 miles of bridge, and the total length needed is around 10 miles. So, the entire bridge would cost at least $1.25 billion. For over 40 years, the biggest problem with this project has been the high cost. Now let's talk about a different idea, an underwater tunnel. In December 2003, Spain and Morocco started talking about building a tunnel under the sea to connect their rail systems. It's similar to the tunnel under the English Channel that links France and the UK. But the Strait of Gibraltar is a lot more challenging because of earthquakes, faults, and strong currents. The tunnel project was on hold for a long time until February 2023, when Spain and Morocco decided to move forward with it. Construction is planned to start in 2030. This tunnel will be 17.7 miles long, going down to a depth of 1,560 feet, and the whole project will take about 15 years to complete. You might wonder why the tunnel isn't just 9 miles long, like the narrowest part of the strait. The answer is simple: it's too deep there. The deepest underwater tunnel now is Norway's Ryfast tunnel, which is 955 feet deep, and that's already very deep. The Gibraltar Tunnel will link Punta Paloma in Spain with Malabata in Morocco. The project is expected to cost around $8.8 billion and could carry 12.8 million passengers each year. It will be a major trade route, moving 13 million tons of cargo between Africa and Europe, and will cut travel time between Madrid and Casablanca to just 5.5 hours. Currently, a flight takes 2 hours, while driving with a ferry takes up to 12 hours. Building a tunnel under the Strait of Gibraltar is considered one of the biggest and most exciting underwater projects in the world. Talking about impossible underwater projects, let us take a trip to Asia. The world's longest undersea tunnel. China is planning to invest a huge $4 billion to build the world's longest undersea high-speed rail tunnel. This impressive project, called the Jintang Undersea Tunnel, will be a remarkable feat of engineering. Right now, there are more than 20 undersea tunnels either completed or in the works around the world. Some of these include the Channel Tunnel between the UK and France, the Seikan Tunnel in Japan, and the Tsushima Strait Tunnel. But the Jintang Tunnel will stand out as the longest of them all. Chinese engineers are set to spend 6 years on this massive project. The news of the tunnel quickly sparked lively debates worldwide. Many Western engineers think this grand plan might be too ambitious and could fail because building such a long underwater tunnel is incredibly challenging. Despite the doubts, China is determined to complete this extraordinary project. They hope to prove their engineering skills to the world by building the longest undersea tunnel ever. The Jintang Tunnel will be a crucial part of the Yangzhou-Zhuhai Railway, showcasing the country's advanced engineering capabilities. The tunnel will stretch 16.2 kilometers long, and it will be buried as deep as 78 meters underwater. The tunnel will be 14 meters wide. To build it, engineers will use various methods, including digging from the surface, using shield machines, and mining techniques. When working in soft, silty ground, a cutting machine digs into the earth. The shield machine helps support the surrounding rock with its strong outer shell. As it digs, the machine moves the soil, gravel, and mud out of the tunnel using a conveyor belt. When the machine hits hard rock, special methods like drilling and blasting are used to break through. To prevent tunnel collapses, the digging is done slowly, with several blasts. When engineers built the undersea tunnel for the Hong Kong-Zhuhai-Macau Bridge, they used a method called immersed tubes. They first built the tunnel sections on land, then placed them on the seabed, and finally sunk and joined them together. The Jintang Undersea Tunnel uses a shield method and is nearly 10 kilometers longer than the Hong Kong-Zhuhai-Macau Bridge's tunnel, making it the largest undersea tunnel in the world. Building the Jintang Tunnel is much harder due to its size and the challenging conditions. The tunnel faces tough conditions, including high water pressure. At a depth of 78 meters under the sea, the pressure is 1 megapascal, which is higher than the 0.7 megapascal that China's previous technology could handle. Even the Hong Kong-Zhuhai-Macau Bridge had a pressure of only 0.8 megapascal during construction. China needs to develop new technology to handle this high pressure before starting the Jintang Tunnel. Once finished, the Jintang Tunnel will be a big achievement for China's infrastructure, showing the country's advanced technology. China has already made impressive infrastructure projects like the Beijing-Daxing Airport and the Hong Kong-Zhuhai-Macau Bridge. These projects prove that China is a leader in infrastructure. The Iron Master. The construction process of the machine is quite simple and easy to understand. It starts by picking up new pre-made concrete sections from the casting yard and moving them to the bridge site, where pillars are already set up. The machine then lowers its support structure, which helps keep everything stable as it stretches toward the first pillar. As the machine moves forward, it carries the beam and then lowers it into place between the starting point and the first pillar. Once the beam is set securely, the machine goes back, bringing along two portable support structures. After picking up another beam, it moves over the first section it installed, and the process repeats until the bridge is done. While the machine, named SLJ-932, reduces the need for human workers compared to cranes, a crew is still needed to watch over the process, clean, and maintain the machine. The crew starts working as the machine sets each new segment, and this continues until the whole bridge is built. This machine has proven to be very efficient, especially in large projects like the Belt and Road Initiative, because it uses fewer human resources, avoids the need for expensive scaffolding, and speeds up construction. Its heavy weight of 580 tons ensures that the bridges it builds can handle loads beyond their maximum capacity, adding an extra layer of safety. The machine has 64 wheels spread across 4 sections, with each section having 16 wheels. It can rotate each section up to 90 degrees, which allows it to move sideways easily when picking up beams. According to reports from bridge design experts, these machines have become more common in China over the last few decades. Initially, each machine was specially made for a specific project, but advances in technology and design now allow engineers to reuse and customize them for different projects. The SJ-932 can build up to 730 spans during its working life. This versatile machine is not just limited to building bridges in cities, it also works in rural areas and is just one of the many machines that have helped China over the years. Kunlun. This is a groundbreaking and powerful bridge construction machine that represents a major achievement in engineering. Developed by a company in China, this huge machine weighs 967 metric tons and is 116 meters long and 9.3 meters tall. It played a key role in building the Mao Bridge, China's first cross-sea high-speed railway bridge, connecting the bustling cities of Xiamen and Fuzhou in Fujian Province in June 2020. Made up of over 15,000 different parts, the Kunlun is not only large, but also very smart. It can perform many tasks at once and was the first machine in China designed for building a special kind of bridge girder called a double L box girder used for high-speed railways. Safety was a top priority during its design, especially for working in tough weather like strong winds. The machine's main girder has an open design that helps it handle windy conditions better. The Kunlun is also equipped with advanced technology like a radar detection system and laser matrix sensors, which allow it to operate precisely even in dark tunnels, and to automatically correct any mistakes when working in large open spaces. In January, an upgraded version of the Kunlun was used in the construction of the Qiwangshan high-speed railway in Anhui Province. This new version can carry beams that are up to 40 meters long and weighs 1,000 tons. The upgrade was a joint effort by the Design Institute and Hunan Heavy Industry of China Railway's 11th Bureau Group. The improvements made the machine smarter and better suited to handling the challenges of bridge construction and power supply in difficult conditions. The new Kunlun is lighter, more energy efficient, and continues to be a shining example of China's rapidly advancing infrastructure, building on the success of its predecessor, the original Kunlun. The wall-climbing monster. This impressive machine is designed to help build tall buildings quickly and efficiently. One of its most amazing features is its ability to climb up the side of a building as workers add more floors. This special ability makes the construction process faster and keeps everything stable, even at heights of over 500 meters. What makes this machine truly unique is its self-supporting platform, which can hold an incredible 2,000 tons. This strong load-bearing capacity allows the machine to keep working even in tough conditions, like hurricane-level winds. The strength of the wall-climbing monster not only improves safety for construction workers, but also lets it operate in bad weather. According to China's state broadcaster CCTV, this machine, developed within China, is expected to speed up the building process by an impressive 20%. This boost in efficiency is a key part of China's ambitious plans to quickly build skyscrapers that stand out on the global skyline. As China continues to lead in construction technology, the wall-climbing monster is a stunning example of the nation's drive to transform its cities at an incredible pace. Tunnel boring machine. Weighing 3,900 tons and boasting 99,900 kilowatts of power, this gigantic tunnel boring machine holds a global record for its massive size. It was developed through a partnership between the China Railway Tunnel Bureau Group and China Railway Engineering Equipment Group, following Chinese design and standards. The machine was sent to Georgia to improve the local transportation system and boost economic growth. This engineering marvel is key to the Kavashedi-Kobe Road project, an important north-south expressway corridor and part of China's Belt and Road Initiative. The project involves building a 9,000-meter-long main tunnel, the largest ongoing infrastructure project in Georgia. Once finished, it will cut travel time from an hour to just 20 minutes, showing China's commitment to fast and efficient construction. While some critics argue that projects like this burden poorer countries with Chinese debt, these machines are undeniably important in the field of construction engineering. However, each machine has a lifespan of about 4 years, allowing it to lay between 700 and 1,000 bridge spans before needing to be replaced. Away from China, let us take a look at some of the biggest machines in the world. Belaz 75710. The world's biggest dump truck, the Belaz 75710, costs $7 million. It comes in different sizes. One model weighs 90 tons and another weighs 130 tons. It can carry 450 tons of material and even handle up to 500 tons with an overload. This earned it a Guinness World Record. It also holds another record for being the largest car by cubic capacity, with 650 cubic meters. The truck is 20 meters long, 10 meters wide, and over 8 meters high. When fully loaded, it weighs 850 tons, which is as heavy as 2 huge passenger planes, the Airbus A380. Because it's so big, it can't be driven on regular roads. Instead, it is taken apart and moved on 20 train cars, taking up an entire train. The Belaz 75710 has 2 massive 16-cylinder engines, each producing 2,300 horsepower, giving it a total of 4,600 horsepower. Each engine has a capacity of 76 liters, making the total over 150 liters, which is about 100 times bigger than a regular car engine. The truck's engines produce nearly 10,000 nanometers of torque. For comparison, a smaller vehicle like a Hilux has about 500 nanometers of torque. The truck's generators produce 3,500 kilowatts of electricity, enough to power 1,000 small apartments. It has 4 wheels, each with its own electric motor, giving the truck a total power of 1,600 horsepower per motor. Since the truck is electric, these motors drive all 8 wheels. Each tire weighs almost 6 tons and costs between $50,000 and $90,000, which is as much as 2 to 4 economy cars. Each tire is 4 meters in diameter and is inflated to 7 atmospheres. If a tire burst, it would make a huge explosion like 3 grenades going off. The truck's fuel tank holds 2,800 liters, which is 55 times more than a regular Hilux. It drives about 100,000 kilometers a year and can be used for 10 to 12 years, covering more than 1 million kilometers over its lifetime. It has 8 air filters that need frequent changing because it works in dusty quarries. The Belaz 75710 was first introduced in 2012. It is made by Belaz and 4 other manufacturers. The truck's top speed is 64 kilometers per hour. Inside the small cabin are 2 seats, an automatic transmission, 2 brake pedals, 1 accelerator pedal, and a cooling system. While it's working, one of its engines runs at 800 revolutions per minute. Liebherr LR130. The LR130 crawler crane boasts a 3,000-ton lifting capacity and has successfully lifted a 3,370-ton test weight at its Ehingen factory in Germany, claiming the title of the world's strongest conventional crawler crane. Designed to lift its maximum load to a 12-meter radius, the 1300 is ideal for applications such as power stations, particularly nuclear plants with large pre-assembled modules, and refinery vessels, where columns can weigh up to 1,500 tons and reach 100 meters in height. Each crawler stands over 3.5 meters tall and weighs over 200 tons. The hook block alone weighs 111 tons. The crane's maximum system length is 246 meters, achieved with a 20-meter main boom and a 26-meter luffing jib. 4 boom configurations can be combined: light, medium-heavy, heavy, and super heavy. According to the manufacturer, the LR11300 is unique for operating without derrick ballast, thanks to its in-house produced slew ring. When used with a derrick, it features an adjustable suspended ballast system similar to the LR-1-3-5-0, which can be guided from a 20 to 30 meter ballast radius. A ballast trailer system is also available, combining the standard suspended ballast setup with a heavy lift modular trailer. For transport, the maximum component weight is 70 tons. Fully equipped with 400 tons of superstructure ballast and 1,500 tons of derrick ballast, the LR300 weighs 3,500 tons. Most components are under 3.6 meters tall and 4 meters wide. The crawler frames, measuring over 3.5 meters tall, 20 meters long, and weighing around 210 tons, are transported after the 82-ton tracks are removed and dismantled. The 128-ton frame is split in half and moved by a low loader. The 4.5-meter diameter slewing ring is transported diagonally to stay within a 4-meter width. To facilitate transport, the concrete ballast blocks are designed to match the dimensions of 20-foot containers. Komatsu D575-3 Super Dozer. Lastly, the Komatsu D575-3 Super Dozer, the world's largest, most productive dozer by a factor of nearly 2. The Komatsu integrated design offers industry-leading productivity, reliability, and additional advanced standard features. Hydraulics, powertrains, frames, and all other major components are engineered and manufactured by Komatsu. Its engine is worth 858 kilowatts, 1,150 Hewlett-Packard turbocharged. The after-cooled engine provides plenty of power. The large blade capacity is 90 cubic meters. The D575-3 Super Dozer reduces operating costs to dollars per ton through high-dosing productivity. The large Super Dozer blade with low dosing resistance and an automatic lockup torque converter saves fuel and increases speed and power transmission efficiency on long pushes. Komatsu's new ergonomically designed control system, PCCS, creates an operating environment with complete operator control. The travel control joystick is ergonomically designed to give the operator a relaxed posture and superb fine control without operator fatigue. Transmission gear shifting is simply carried out with the thumb. Fully adjustable suspension seat and travel control console for improved rear visibility during the return part of the cycle. The operator can adjust the seat 15 degrees to the right. The transmission and steering controls move with the seat for the best operator comfort. The travel control console also has adjustments for aft and height, with an independently adjustable armrest. Each D575-3 operator can adjust control positions to his individual preference. The engine revolution is controlled by an electric signal, providing ease of operation and reducing problems caused by linkage joint seizures. The blade control joystick uses proportional pressure control, a PPC valve, and a palm command joystick, similar to the travel control joystick. Combined with the highly reliable Komatsu hydraulic system, PPC control enables superb fine control. The D575-3. Superdozer uses a newly designed powertrain electronic control system. The controller registers the number of operator control movements of the lever, the operation of switches, and machine condition signals from each sensor. It calculates to accurately control the torque converter, transmission, steering clutches, and brakes for optimized machine operation. The controller automatically adjusts each clutch engagement depending on travel conditions, such as gear speed, revolution, and shifting pattern. This provides no shock, smooth clutch engagement, improved component reliability, expansion of component life, and operator riding comfort. The large tinted glass windows provide a panoramic view of the work area. An air filter and higher internal pressure prevent dust from entering the cab. The constant machine condition check helps prevent severe problems and lets the operator concentrate on the controls. When an error occurs during operation, the user code and service meter are displayed alternately. When a high-importance user code is displayed, a caution lamp lights up, and a warning buzzer sounds to prevent the development of serious problems. The fuel-efficient Komatsu engine and the heavy machine weight make the D5753 Superdozer a superior crawler dozer in dosing production. The engine is designed to surpass the Environmental Protection Agency and California Air Resources Board regulations and features direct fuel injection, a turbocharger, and an aftercooler to maximize fuel efficiency. The engine is mounted to the main frame with rubber cushions to minimize noise and vibration. For greater efficiency during long pushes, the lockup mode allows the system to engage the torque converter lockup clutch automatically. Locking up the torque converter transmits all the engine power directly to the transmission, increasing ground speed and thus achieving efficiencies equal to a direct drive. The system provides powerful traction, component durability, and operator comfort. Outstanding traction can be achieved because the shoes follow the ground's contour. The X-shaped bogie structure, a resilient equalized undercarriage, performs independent seesaw movements. Rubber shock absorbers are mounted on the X-shaped bogies to decrease vibration and shock. The bogies and rubber cushions provide different absorption characteristics depending on the ground surface. The remote electric unit is a conventional rigid undercarriage when the machine travels flat ground. The REU maximizes the suspension effect when the machine travels on uneven ground. The standard equipment includes a function for selecting travel speed presets, allowing the operator to choose from 3 preset patterns for fore and aft travel speeds: F1-R2, F2, and manual shift. If the F1-R2 or F2-R2 preset pattern is selected and the travel control joystick is moved forward or rearward, the machine will automatically travel at the F1-R2 or F2-R2 speed. This feature reduces operating hours and the time the operator shifts gears during repeated round-trip operations. The auto shift-down function controller monitors engine speed, travel gear, and travel speed. When a load is applied and the machine's travel speed is reduced, the controller automatically shifts to the optimal gear speed to ensure high fuel efficiency. This function allows for comfortable operation without manual downshifting, ultimately increasing productivity. Thanks for watching. See you in the next video.